All right, we are going to talk about Gauss's law. I can't spell today. All right, Gauss's law, Gauss apostrophe law. So Gauss's law, basically, it came around because when we were looking at our previous discussion with flux, we said, okay, so flux is how much of the electric field is actually crossing perpendicular to the surface. All right. So we said flux is electric field dot area vector. All right. So that was flux. Well, that's okay if all the lines are parallel and things like that. But what happens if you want to know more? What happens if it is a non-uniform field? What happens if you have a object that has interesting shapes, dimensions, things like that? So let's just go real simple. What happens if we have a point charge? All right, so we got a point charge. If I look at the field lines coming from that, well, obviously it's all the way around. I guess I'm going to draw a x-wing here. So if I look at the electric field here, if we were to draw a same Gauss, same rectangle, if you will, these angles are not going to be the same because they're going to keep changing. We have an infinite number of field lines in here, and they'll keep changing their angle. So that's where we would have to go to the integration of this. So to just get this, we'd say, well, that is the integral of E dot dA. All right. So dude named Gauss said, okay, well, how do you figure out what this really boils down to? And so what if we chose a different shape? Because in theory, we're choosing the shape. The shape is kind of imaginary. It's an imaginary point in space. And so if we want, we could say, you know what, instead of using a flat surface to determine the amount of the electric field that's passing through this surface at a certain distance and things like that, what if we chose a better shape? So if we look at a point charge again, then we would have the field lines all pointing out. All right, we've done this before in the past. So electric fields point out like this. Well, what if I chose a sphere? Now, obviously, I'm just going to draw a circle here very much. All right, there's my best sphere. If I chose a sphere, then if I look, all right, let's zoom in, see how my art skills were. At each point, that electric field is hitting it at a right angle. All right, at every single point, that electric field is crossing the surface at a right angle. So by choosing a sphere, then I will always have my perpendicular nature, all right, in my EDA. So what's really happening here is we kind of have a new start. And so instead of just doing the integral of E dot dA, we're going to actually do this. E dot dA. So you might be saying, well, isn't that the same thing? Yeah, well, it's kind of the same thing. And this would be the total flux is equal to E dot dA. But you'll notice that what we're doing here with this right here, this is closed surface integration. So we're not integrating from one spot to another. We're saying, no, I've made a complete closed surface. So I'm just going to calculate the total area of that surface. So in a way, we're cheating. It's like saying, well, integration's always calculating the totality of something. Well, what if it's a defined shape, like a sphere? That is a defined shape. We have a defined equation to just flat out calculate surface area. So that way we don't really need to crunch a ton of numbers. It's going to make our lives easier. So let's do that. So if it is a sphere, then we know that the area of that sphere is going to be 4 pi r squared. It's just a fact. Where r is obviously the radius of our sphere. Now, we also know that the electric field of a point charge is defined as kq over r squared. So if we are going to multiply these two things together, then this then becomes closed integration kq r squared, the dA. So I should really erase this because we've already integrated to calculate the totality of the surface area. So we got kq over r squared times 4 pi r squared. Some stuff's going to cancel out on us. So we get kq times 4 pi. Now, we do remember from earlier discussions that k is equal to 1 over 4 pi epsilon naught, because epsilon naught is equal to 1 over 4 pi k. All right. So if we want, we can actually do some substitutions. So right here, I'm going to throw this guy over here where it says k. Doot. And I don't need to worry about that bad boy. Sometimes they'll show up, but don't need to worry about it. And so then, if I do that, I get 4 pi times q over 4 pi epsilon naught. So now my 4 pi's die. Now this q is also very interesting because this q right here, this is the enclosed charge. So that is the charge has been enclosed by our surface, which we are going to refer to as a Gaussian surface. All right, so it's a surface that we have chosen that's going to allow us to contain all of the appropriate charge and thus all of the flux. So this Q is Q enclosed, all the enclosed charge, so we call that Q enclosed. So when you kind of go down this derivation, what you really see is that the total flux is defined as the closed integral of E dot dA, which is then equal to the enclosed charge within that surface divided by epsilon naught. This right here, that's Gauss's law. All right, that's kind of a big deal. We're going to be using that a lot. So to that end, we're just going to do one example of how we can use Gauss's law. Now you can do it in any shape you want. So I'm going to look at it through the eyes of a wire. All right. So let's go through and we'll just do it. There's Gauss's law hanging out for us. We're going to do it in the eyes of a wire. So here we have a nice wire. I have length L. All right. And I'm going to say, all right, we're going to make it infinitely long. Now, the perk of me making it infinitely long is I don't have to deal with what's happening out of the end caps. All right, so I've got a wire. It's infinitely long. And if we look at the field lines, they're going to be coming out of all directions equally. Should draw them the same length, but I'm human. All right, so they're going to be coming out the same directions radially. All right, covers everything in between. So if we want to pick a shape that will encompass all of this charge and every single field line will hit that at a right angle, well, the shape to pick is a cylinder. So if I pick a cylinder, go 3D art skills, then this will always be hitting all of the field lines at a right angle. Up, down, left, right, whatever angle it is, it'll hit that angle. And so then I have to ask myself, okay, so how do I use Gauss's law? Well, step one, always rewrite it. I highly recommend that. Oh, dogs found someone. Pause. All right, dogs are back. Dealt with that. All right, let's see, where were we? Where were we? Sorry about that, guys. So let's say we've got a wire. It has a linear charge density across the entirety of the wire. We are going to use Gauss's law to try and figure out what is what is the electric field strength at some given distance r. All right, that's what we want to find out. Again, r would be what we chose as our radius for the Gaussian surface. So let's write out the equation. Let's get rocking and rolling. So we've got the total flux, E dot dA, which is equal to Q enclosed divided by epsilon naught. Now, if we look at the shape, the only part of the dA that we care about is this edge here, all right, and how that goes around. So this side edge, that's all we care about. We do not care about the end caps because the field lines will always be parallel to those end caps. So no part of those field lines is crossing through one of these two end caps, but it is going through the sides. All right, it's going through this surface right here. It's all crossing through that. So that's the surface area that we are going to care about. Now, since it is a uniform charge density, we know that that is also equal to the total charge enclosed per unit length. All right. And so now we're just going to start doing our replacement. So we've got E is what we're looking for. dA, well, that's the total surface. That's the total surface area. And since it is a cylinder, the length times width, well, the length is L. The width is going to be 2 pi r because that is your circumference. So we've got E times that is going to be equal to our total enclosed charge. Well, if we rearrange this guy, Q enclosed is going to be equal to lambda times L. So we've got lambda L over epsilon naught. So now I can kind of start going to work, do some rearranging here. So let's do that. L's go bye-bye. And then E is equal to a fun divided by epsilon naught. So E equals lambda over 2 pi r epsilon naught. All right, so that's what that is equal to. But we could also, if we want to, we could write it in terms of K because we know that epsilon naught is equal to 1 over 4 pi K. So I can replace that. And so then that would give me 4 pi K lambda over 2 pi r. And now even more stuff cancels out. We always try and get as much to cancel as possible. So we get K lambda over r. And this would be the strength of the electric field along the entire length of that wire, which is so much easier than some of the derivations that we've done